Hello, and welcome to Differential Equations. This is Lecture 13, Undetermined Coefficients. Last time, we saw that if L is a linear differential operator, then the general solution of the non-homogeneous equation Ly equals F is given by y of t equals y part of t plus y home of t, where y part of t is any one solution to this equation, and y home of t represents the general solution. But to the homogeneous problem, Ly equals 0. This time, we're going to talk about one particular method to find one particular solution. Okay, so the method of undetermined coefficients is a way to find particular solutions of certain non-homogeneous equations for y equals F. So here, we will want L to be constant coefficient and linear. And we will want F to be built up from t sine of some angle, say omega times t, cosine of omega times t, e to the at, where we allow omega and a to be constants. We allow sums and products of these functions, but we do not allow compositions or quotients. So, for example, it will work if you have if you have f of t is equal to cosine of t, or you have f of t is t to the 5, or you have f of t is e to the minus 6t, or you have f of t is e to the t times cosine t plus t to the 11 times sine t minus 256 times sine of 3t cubed, or f of t is e to the t minus 2t cosine 5t. So all of these are fine because they're obtained from functions like these by multiplying and adding. However, it will not work for f of the forms. So say you had f of t equals e to the t squared, right? That won't work. F of t equals tangent t, f of t equals cosine t divided by t, right? So cosine t times t is fine. Cosine t divided by t is not fine, right? Not that there's anything wrong with those forcing functions, it's just that this particular method will not work. Right, so what is the method? Well, we'll see two versions. Right, so this is the first, what we'll call the naive version. Right, naive in the sense of innocent, right, or where you're ignoring some relevant details, but that's okay. So the method says if Ly equals f is a non-homogeneous linear equation with constant coefficients, and f is given by sums and products of exponentials, sines and cosines, and polynomials, then to find a particular solution, right, you make an educated guess. Right? Or if you want to be fancy and use the German word for educated guess, Ansatz. For y of t in the same form as f of t with undetermined coefficients, right? These are constants that you want to find. So constants to be determined. Substitute your guess into the equation, and then solve for the coefficients. Right? So the point is, when we're looking for a particular solution, we don't need to find all of the particular solutions. We just need to find one. So you might as well make an educated guess and hopefully find one, right? And why is this an educated guess? Well, the point is, if you look at the right-hand side and it's, say, e to the t, then, well, the left-hand side, you're going to take some function, you're just going to take some derivatives and add, multiply with constants and add. So if that's going to end up being an e to the t, the function you plugged in has to be something like e to the t, right? So it's a very reasonable guess to make that you have some constant times e to the t, and then you just have to figure out the constant, right? Let's work out an example. Right, so suppose we want to find a particular solution of the equation y double prime plus 2y prime equals sine of 3t. Okay, so the first forcing term is f of t equals sine of 3t. So we make an educated guess. And look for a solution of the form y of t is going to be some constant times sine of 3t plus some constant times cosine of 3t. Okay, so of course here I just have a sine of 3t. So you might think, well, why don't you just guess a multiple of sine of 3t, right? And okay, well, let's think about that. If you're going to be taking derivatives, right, however many derivatives, and you start with sine of 3t, then whenever you take an odd number of derivatives, you're going to have some cosine of 3t, right? On the other hand, if I start with a linear combination of sine of 3t and cosine of 3t, and I take any number of derivatives, I still have a linear combination of sine of 3t and cosine of 3t, right? So this expression is closed under differentiation. So it's a much better guess than just plugging in sine of 3t or just plugging in cosine of 3t. Okay, so that's why we guessed something like this. So let's try it and see. So to substitute, let's start by computing y prime of t would be 3a cosine of 3t minus 3b sine of 3t. And then y double prime would be minus 9a sine of 3t minus 9b cosine of 3t. And so when we plug it into the equation, y double prime plus 2y prime, we end up with, here's y double prime and 2y prime. So I'll put together the signs. So I have minus 9a in the second derivative, and then plus 2 times the first derivative. So I'd have minus 6e sine of 3t. And then, so I take care of the sines. Now let's put together the cosines. So I'll have plus minus 9b, and then plus 6a cosine of 3t. Right, so that's what I get from plugging in our guess, our ansatz, to the left-hand side of the equation. And then I want that to be equal to, so I'll put in equality with a question mark on top. I want that to be equal to sine of 3t. So now let's just compare coefficients, right? So we need minus 9a minus 6b should be equal to 1. and minus 9b. Actually, let me put these in the opposite order. So first 6a minus 9b, that should be equal to 0. Right? This is a simple system to solve. Let's just multiply the first equation by 3. Multiply the bottom equation by 2. Right? So that I have minus 18b on both. So then if I subtract the bottom equation from the top equation, I end up with minus 39a equals 3. Right, which tells me that a is equal to minus 1 over 13. And then solving this equation for b, I get b is equal to 2a over 3. So that makes b equal to minus 2 over 39. So success. A particular solution is y of t equals minus 1 over 13 sine of 3t minus 2 over 39 cosine of 3t. Okay. We can make a little chart of what you should guess. So our naive guesses. Right. So if f of t has the form then look for a particular solution of the form. Right. So for example, if f of t has the form e to the at, then you should look for a particular solution. Let's call this f1 and this y1. A times e to the a little a times t, right? F2, if the forcing function has the form of polynomial of degree k, then let's call it y2. What you should look for is, well, try a general polynomial of degree k. Right? Call this piece of k of t. Right? So it doesn't really matter what form the polynomial the forcing function has. If you just care about its degree, if this has degree k, then you should try a general polynomial of degree k. Okay? Let's call f3. What happens if you have like a cosine of omega t or a sine of omega t? Well, then, just like in the example we did a moment ago, you should try a times cosine of omega t plus b times sine of omega t. Right? And what happens if you have, let's say, a product, so f1 times f2, right? So what if you have an exponential times the polynomial of degree k? Well, what you should try is y1 times y2. So just try an exponential times the general polynomial of degree k, right? And similarly for the product of any other ones of these, if you have f1 of t times f3 of t, right? So that is to say, if you have a cosine of omega times an exponential, then what you should try is y1 times y3, right? So go ahead and try an exponential times this combination of cosine and sine. And also, if you had a product of f2 with f3, you should try y2 with y3. Okay, so perfect. So this is just how to set up some naive guesses. Now, it won't always work, and that's why we keep using that word naive. What makes this naive is that in the equation that we're trying to solve, right, Ly equals F, we're focusing on the F and ignoring L, right? So let's do an example where this would lead us wrong. Suppose we wanted to find a particular solution of y prime minus 3y equals e to the 3t. Okay, so here, I'll put it in parentheses. Here, L of y would be y prime minus y minus 3y. Okay, so perfect. We look at our chart. The forcing term is e to the 3t, so that's a f1, so we should try a y1. Right, so naively, we try, and because I know it's not going to work, I'm going to call it y tilde. So we try to use y tilde equals a times e to the 3t. But if we plug it in, right, L of y tilde, right, y tilde minus y tilde prime, so minus 3y tilde, we get 0, right? So our potential particular solution didn't work because when you plug it in, you didn't get anything on the right-hand side, so you can't make that equal to 3t by choosing your constant cleverly. Right? So this will never work. Because y tilde solves the associated homogeneous equation. Right? L of y tilde is equal to 0. Okay. So with that in mind, we need to improve our method of undetermined coefficients. Okay. So here's the method in an improved version. So again, same setup. If Ly equals F is a non-homogeneous linear equation with constant coefficients, right, as above, so F is still one of the kinds that we were looking for before, then to find a particular solution, use the naive guess for y unless one or more terms of your guess satisfy the associated homogeneous equation. Ly equals 0. In that case, multiply those terms by the smallest power of t. It guarantees that they no longer satisfy the homogeneous equation. Okay, so let's come back to this example. We have y prime minus 3y equals e to the 3t. So our naive guess, y tilde of t equals a times e to the 3t, didn't work because this satisfies the homogeneous equation. So if you plug this into the left-hand side, you get 0. And now we have our improved guess. Our improved guess is just take our naive guess and multiply it by t. So we have a times t times e to the 3t. Substituting, we get y prime of t equals a times e to the 3t plus 3a times t e to the 3t. So if you plug this into the equation, y prime minus 3y, we get a e to the 3t plus 3a t e to the 3t. And then we subtract 3 times y. So 3at e to the 3t, right? And notice that this term cancels with this one. So we're left with a e to the 3t. We want that to be equal to 1. No, sorry. We want that to be equal to e to the 3t, right? To the right-hand side. And so that means we just need to set a equal to 1. And hence, y of t equal to t e to the 3t is a particular solution. Let's work out another example. So now suppose we have q double prime plus 9q equals sine of 3t. Our naive guess would be q tilde of t equals a cosine 3t plus b sine of 3t, right? Because the right-hand side is sine of 3t, our forcing function, and so we should try a linear combination of cosine of 3t and sine of 3t. But L of q tilde is equal to 0, where L is the linear operator given by the right-hand side of this equation. So we need an improved guess. Our improved guess in this case would be q of t equals a times t cosine 3t plus b times t sine of 3t. Okay, so now we have to substitute this in. So let's start by computing the derivative of q. Right, the derivative of q, we use the product rule for derivatives, right, also known as the Leibniz rule. And so we have a term when the derivative hits the t, and a term when the derivative hits the cosine. And similarly, over here, we have a term where the derivative hits the t, and a term where the derivative hits the cosine. Sorry, the sine produces cosine, right? And so we keep going like this to compute the second derivative. So this term would give us minus 3a sine of 3t. Then this next term will give us minus 3a sine of 3t minus 9a t times cosine 3t. And then similarly, we get 3b cosine 3t plus 3b cosine 3t minus 9b times t sine of 3t. Right? Or grouping like terms, minus 6a sine of 3t minus 9a times t cosine 3t plus 6b cosine 3t minus 9b t sine 3t. Okay, so then if we compute q double prime plus 9q, we get minus 6a sine of 3t. Then this 9q, so 9 times this is going to cancel this term and it's going to cancel this term. So we're just going to be left with that one now. So plus 6b cosine of 3t. And then we want this to be equal to sine of 3t. And so we see that what we need is minus 6a should be 1 and 6b should be 0. So q of t equal to minus 1/6 t times cosine 3t works, right? Works. It solves this equation. We found our particular solution. Okay. So now let's do an example where we're asked for the general solution. Right? Suppose we want to find the general solution of the equation y to the 4 derivatives minus 2y 3 derivatives plus 2y double prime minus 2y prime plus y equals t plus 5 times sine of t plus 3e to the t plus 2t e to the t. Okay, so if we write this equation as Ly equals f, then since L is linear, we know that the general solution can be written as y is equal to y part plus y home with y part a particular solution and y home the general solution of L of y equal to 0. Okay, now we know how to find the general solution of Ly equal to 0, right? We compute the characteristic polynomial. The characteristic polynomial in this case is r to the 4th minus 2r cubed plus 2r squared minus 2r plus 1, right? And this factors as r minus 1 squared times r squared plus 1, right? So you can further factor that into r minus 1 squared times r minus I times r plus I, right? So the general solution for the homogeneous equation L of y equal to 0 is, I'll call it y home. So C1 times e to the t plus C2 times t e to the t, right? So that's because of this factor, the r minus 1 squared. So 1 is a root with multiplicity 2. So that means you have to include an e to the t and a t times e to the t, right? Next, we have these complex conjugate roots, I and minus I. So we could include e to the it and e to the minus it, or we could include cosine t and sine t, which is what we'll do. So here I can write C3 times cosine t plus C4 times sine t. Okay, so that's the general solution of the homogeneous equation. So now we just need to find a particular solution. Since our forcing term is equal to t plus 5 times sine of t plus 3 e to the t plus 2t e to the t, our naive guess is, so I'll label it naive, right? So y tilde of t, right? So because of this t, we should try a polynomial of degree 1. So let's call it a1 plus a2t, right? Then sine t, so I should include some constant times sine t plus some constant times cosine t. And then I have here a polynomial of degree at most 1, well, degree 1 times e to the t. So I should include a polynomial of degree 1 times e to the t, right? So these two terms came from this one. These two terms came from this one. And then these two terms came from these two. Right? So this is our naive guess. Right? Now, we know that we need to watch out for elements in our naive guess that satisfy the homogeneous equation, right? And we just wrote down the general solution of the homogeneous equation, right? So let's improve this to a better guess. So these terms, they do not satisfy the homogeneous equation, so I don't need to change those at all. I'll keep them as they are, a1 plus a2t, right? However, sine t and cosine t, those do satisfy the homogeneous equation. So they're not going to be useful at all for finding a particular solution as they are. I should multiply them by t so that they remain useful. Right? And then over here, e to the t and t times e to the t satisfy the homogeneous equation. So neither one of these terms is useful. So I need to multiply them by t. So in fact, this first term, I need a t squared e to the t, and then a t cubed e to the t. Right? Because anything less than t squared would satisfy the homogeneous equation. So this is our improved guess. And if you substitute in, I'm not going to do the algebra here, but you'll find that 2 plus t plus 5 over 4 t sine t plus 1/4 t squared e to the t plus 1/6 t cubed e to the t works. And so the general solution is y equals yp of t plus y home of t, right? Where this is the particular solution that works, and here is the general solution of the homogeneous system. Okay, so you can stop watching there if you like. Next, I'm going to talk about some historical context. Right? In this case, I'll tell you a bit about Leonhard Euler. Right? This will not be on the homework or the exam, so you can stop watching if you like. Okay, so Leonhard Euler lived from 1707 to 1783. So for context, Newton died in 1727, and Leibniz died in 1716. So Euler was the Euler's life overlapped with theirs, but he wasn't really a contemporary. In fact, when the year Newton died was the year that Euler was finishing his studies. So they didn't really overlap in terms of academic work, but you can see that Euler is like the generation right after Newton and Leibniz stopped working. Euler was born in Basel in Switzerland, right? So Basel has already come up because this is where the Bernoulli family lived. And it's where Jakob and later Johann Bernoulli were professors of mathematics, right, at the University of Basel. So first Jakob, who was the older brother, and then when he died, Johann Bernoulli took over his chair. So Euler's father, Peter Euler, lived with Jakob in Jakob's house, together with Johann, when he and Johann were undergraduates at the University of Basel. And both of them studied math with Jakob Bernoulli. So Peter studied math, but he graduated with a degree in theology, and he worked as a Protestant minister right outside of Basel. Euler was born in Basel, grew up very close by, and at age 14, he started attending the University of Basel. His father wanted him to be a minister as well, so he was studying philosophy and theology. But in his free time, Euler would work on math. And he would get Johann Bernoulli, who was now professor, so Jakob was already dead, but Johann was professor, to help him with his study. So what he would do is Johann would tell him what books to read, and then Euler would go see him on Sundays to ask him questions about what he had read. After Euler had gotten his master's degree, he managed to convince his father to let him study mathematics instead of theology. And this ended up working when Johann Bernoulli paid a visit to Peter Euler, his old friend, to explain to him that a talent like Euler's really should be allowed to study mathematics. Euler was a close friend of Johann's sons, Daniel and Nicolaus Bernoulli. When Euler finished his studies in 1726, he started looking for an academic job. His friends, Daniel and Nicolaus, had been recruited by Peter the Great a couple years earlier to teach at the newly founded St. Petersburg Academy in St. Petersburg in Russia. Nicolaus was teaching mathematics and physics, while Daniel was teaching physiology. Nicolaus died in 1726 of appendicitis. Daniel took his job and arranged for Euler to be hired to teach physiology. Right now, Euler knew mathematics and he knew philosophy, theology, but not physiology. But that's okay. If that's what it took to get an academic job, Euler was willing to do it. He put in the work. He took courses in medicine, and he went to Russia to take up his position in physiology. Once he arrived, though, he was pretty soon after able to transfer his position to the math department, so he was teaching mathematics. However, he did make use of the medicine and physiology he had learned, he served as a medical lieutenant in the Russian Navy for a few years. When Daniel Bernoulli left Russia in 1733, Euler was promoted to the senior chair of mathematics, and the financial improvement in his new position allowed him to marry. He married Katharina Gesell, who was also Swiss, living in St. Petersburg. They had 13 children together, but only 5 of them survived infancy. Remarkably, Euler was able to work while surrounded by small children. They would be playing noisily, or he would often be rocking a baby with one hand while working out math problems with the other. Much later, he would be blind, and he would be playing with grandchildren on the floor while simultaneously dictating mathematics papers to his assistants. So Euler was remarkable in many ways. In 1735, Euler suffered a bad fever and he almost died. He also started having problems with his eyesight. And as I mentioned a moment ago, he would eventually go blind and continue carrying out computations in his mind, intricate computations with like 15 significant digits. Peter the Great had died before Euler arrived in Russia. When Peter died, he was succeeded by his wife, Catherine I, then by his grandson, Peter II, and then by his niece, Anna. Anna was the daughter of Peter the Great's older brother, Ivan V, so he had been co-emperor with Peter. And the rivalry between their descendants was a big deal, and it came to a head. It led to a lot of political instability when Anna died in 1740. So Empress Anna's designated heir, Ivan VI, her grandnephew, right? This was a descendant of Peter the Great's older brother, Ivan V. But Ivan VI at the time was only 2 months old. And you never want to have a young baby as a monarch if you want stability. So in fact, he was captured, locked up in a dungeon on the orders of a daughter of Peter the Great, Elizabeth, who then became empress. And Ivan VI would spend all of his life in captivity. Elizabeth, when she became empress, she swore to never sentence anybody to death, and she kept that promise. Although this did not mean that she was kind. There was a lot of cruelty, but she never put anybody to death judicially. Ivan VI, though, stayed in captivity his whole life. He was eventually murdered on the orders of Catherine the Great a while later. But in any case, when Anna died in 1740, there was a lot of political turmoil. This made St. Petersburg very unwelcoming to foreigners, and Euler left. He had been invited by Frederick the Great of Prussia to join the new Academy of Science in Berlin, and Euler went. He spent the next 25 years in Berlin, and those were the most productive years of his life. And a very productive life, actually. It's when he's in Berlin that he writes his textbook, Introductio in Analysis Infinitorium, which means Introduction to the Analysis of the Infinite. This was published in 1748, and it was an extremely influential textbook. A lot of the notation that Euler used just became standard notation from then on, because everybody had studied from Euler's textbook, and so everybody was familiar with that notation. That just became the notation they used. Some of this notation, not all of this is from that one textbook, but a lot of it is he introduced the letter E, what we call Euler's constant. He wasn't the first one to use pi for, say, the area of the unit disk. This had been used before, but it's Euler that popularized it. It was after Euler that it became the standard notation. He also introduced the notation I for the imaginary unit. He introduced capital sigma for summation. He introduced the concept of a function and also the notation we use, f of x. That's his notation. Logarithms. The modern notation for logarithms and the way we think about them. If you go back to when logarithms were invented, it's sort of it's a bit backwards to how we use them today. It's a little confusing to translate, but it's starting with Euler that they get used the way we use them. He also was the one to start using like delta, capital delta for change. So for like the difference in y as delta y. Right. So Euler's in Berlin. He initially he was very happy in Berlin. He had great reception. People were very excited to have him there. But later he was unhappy. The thing is that Frederick preferred to have people in his academy who were also good dinner guests and good courtiers. For example, Voltaire was there and a favorite of Frederick the Great. He was very witty. Euler, not so much. A bit later, Euler was passed over when the presidency of the academy became available. Worse, the academy was offered to a scientific rival of Euler, D'Alembert. And so Euler decided to return to Russia. This wasn't too hard to arrange because Euler had maintained close connections with the St. Petersburg Academy during his years in Berlin. Right, so the Princess Elizabeth, the Empress Elizabeth, had died in 1762. She was succeeded by her nephew, Peter III, but just like 6 months into his reign, Peter III was deposed and murdered on the orders of his wife, who ruled as Catherine II and is known as Catherine the Great. Euler was offered a fantastic position in St. Petersburg and returned there in 1766. Euler became basically blind due to a cataract in 1766. He had already lost vision in one of his eyes, his left eye, I think, much earlier, back when he had that fever, but now he lost vision in the other eye. He's supposed to have said, after he became blind, that, well, now I will have fewer distractions. So, fantastic attitude. He stayed in Russia until he died from a brain hemorrhage in 1783. Amazingly, despite his blindness, Euler produced almost half of his total works after returning to Russia. Euler is easily in the running for the greatest mathematician of all time. He contributed to all areas of mathematics. There's a common joke that a mathematical result is named after the first mathematician after Euler to discover it, because Euler discovered so much. People have said of Euler that he did mathematics with the ease with which other people breathe or with which birds fly. Pierre-Simon Laplace, who was a brilliant mathematician who did not suffer from an excess of humility, would tell young mathematicians that they should read Euler. He is the master of us all. Euler is considered to be the most prolific mathematician ever, with over 860 publications. Journals were still publishing articles submitted by Euler 30, 40 years after his death. Some of the things that Euler did that are related to this course include formulating Newtonian mechanics using calculus, right? I mentioned when we were talking about Newton that Newton discovered calculus, but that's not what he would use for his presentations. When Newton presented results, he would present them using more classical mathematics. He used calculus for discovering results. So it's Euler who just took the point of view that you should just be using calculus for everything and described how to formulate Newtonian mechanics using calculus. This was a sea change in mechanics. He identified the conditions for exactness of differential equations. He developed the theory of integrating factors. He's the one who found the general solution of linear ordinary differential equations with constant coefficients and figured out what to do for both homogeneous and non-homogeneous equations. And of course, he came up with the Euler method that we saw for approximate solutions. Things that we haven't covered that he did that are related. He made frequent use of power series to describe solutions of differential equations. He made very important contributions to partial differential equations, and he gave the first systematic treatment of the calculus of variations. Calculus of variations is very closely related to things like the brachistochrome problem and the tautochrome problem, where you're trying to solve an optimization problem, but instead of looking for a number, right, the value at which a function achieves its maximum, you're looking for a function itself. So you're looking like which function describes the curve of fastest descent, for example. Euler has tons of results. Among some that are easy enough to talk about, right? There's Euler's formula. Right, this has already come up. E to the I theta is cosine theta plus I sine theta. Right, the particular case, e to the I pi plus 1 equals 0. This has often been called the most beautiful equation in mathematics, right? Because you're combining all of the most important constants in math in a single formula. Another really important contribution he made is known as the Kennisburg bridge problem. Right, so Kennisburg is a city in what was then Prussia, and there's a river, and then there's an island in the river, and then the river goes on like so, and then there's land over here, and there were 7 bridges connecting these different pieces of land. And apparently, every Stadfest, so every festival of the town, it was a common thing to do, to try to cross all of the bridges without repeating, right? And nobody had been able to do it, and so Euler gave an explanation of why nobody had been able to do it. So he pointed out that trying to cross all of the bridges without repeating is like trying to draw this figure. So let's put 3 dots here and 4 dots here, a 4th dot here, and then connect these with vertices, sorry, with edges, if there is a bridge, right? And so trying to cross all of the bridges without repeating is like trying to draw this graph without repeating an edge, right? So now it's known as an Eulerian trail. Is in any graph, try to draw a path that covers all of the edges without repeating, right? And Euler, in a very nice paper, it's very easy to read, he showed that such a thing exists if and only if there are exactly 0 or 2 vertices that have odd degree. Right? So the degree of a vertex is how many edges are coming out of that vertex. And so you can think that if you have an Eulerian trail, then every time you go to a vertex, you have to leave it, unless it's where you're starting or where you're ending, right? So that means that every time you get to a vertex, you have to leave. But since you don't want to repeat edges, that means that every vertex should have an even number of edges, because I have to be able to arrive and leave, right? But the exceptions can be in the vertex where you're starting and the vertex where you're ending. So if you have exactly 0 or 2 vertices that have odd degree, then you have an Eulerian trail, and only if. And here you do not. So that's why nobody had been able to do it. This problem is extremely important, or Euler solution rather, because it starts graph theory and it starts topology. Topology is the study of those geometric properties that don't change when you make continuous deformation. So they don't depend on lengths and they don't depend on angles. right? So things like this about whether or not there exists an Eulerian trail doesn't depend on the lengths of the bridge or the angles between the bridges. So it led to the development of topology. Another result of Euler that led to a lot of important things in topology is the Euler characteristic. This means something in topology now, but for Euler, this just said that if you have any polyhedron on a sphere, so for example, a die, right, a six-sided die, or if you've played things like Dungeons and Dragons, and a four-sided die, and an eight-sided die, and a 20-sided die, and whatever, if you have one of those polyhedra, then the number of vertices minus the number of edges plus the number of faces is always equal to 2. Right? That's because the polyhedra are basically triangulations of spheres. Right? It turns out that the 2 is because you're on a sphere. If you did the same thing on a torus, you would have a 0, and if you did the same thing on a donut with 2 holes, you would have -2, and so on. So this is very important in topology. And the last thing I'll tell you about is Euler's solution of the Basel problem. Right? So it's named after the city in Switzerland that Euler was from and that the Bernoullis were from, and that's why it's named the Basel problem, because of all of these people. So the Basel problem, it had been known for a long time that the sum of 1 over k squared, where k goes from 1 to infinity, was finite. Right? But nobody knew what it converged to, right? So it had been known already. There's a mathematician called Pietro Mengoli, who in 1650 pointed out that this series converged and asked for what it converged to. Many mathematicians, including Leibniz and the Bernoullis, tried and failed to figure out what this converged to. Euler became famous when in 1735, when he was 28 years old, he figured out what it converged to. In fact, Euler simultaneously figured out what the values of the sum 1 over k to the 2n converge to for all natural numbers n. He did this by factoring a power series as if it were a polynomial. So you remember we talked about how for a polynomial, if you know what the roots are, then you can factor the polynomial, right? So if a polynomial vanishes when x is equal to 2 and when x is equal to 3, then you know that x minus 2 and x minus 3 divide that polynomial, right? So Euler just took an infinite series and factored it as if it were a polynomial. This doesn't work in general, and Euler didn't justify it. This was before a rigorous approach to calculus and analysis. But the case that Euler did, this particular power series, it does factor the way Euler factored it. It just took a long time. It took until Karl Weierstrass until that could be justified. Okay, so here's what he did. So let's start with the power series expansion for sine, right? Power series expansion for sine, or Taylor expansion at 0, is x and then minus x third divided by 3 factorial, then plus x to the 5 divided by 5 factorial, minus x to the 7 divided by 7 factorial, and so on, right? So I just have the odd powers of x always multiplied by the appropriate factorial and with the sign alternating, right? If I divide by x, right, then sine of x over x, I get 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, and so on. Okay, now when does sine of x vanish? So the zeros of sine x over x are well, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, so on. So we can factor sine x over x as 1 minus, well, really, we would have some constant times 1 minus x over pi, 1 plus x over pi, right? So that accounts for the zeros at plus or minus pi. Then the zeros at plus or minus 2 pi give us 1 minus x over pi, 1 plus x over 2 pi. Then the zeros at plus minus 3 pi give us 1 over x divided by 3 pi, 1 plus x divided by 3 pi, and so on, right? And multiplying contiguous factors together, I get 1 minus x squared divided by pi squared, 1 minus x squared divided by 4 pi squared, 1 minus x squared divided by 9 pi squared, and so on, right? So I left this constant a because when you know the roots of a polynomial, then you know that these things factor it, but that still leaves some multiplicative constant undetermined. However, in this case, from knowing that the limit when x goes to 0 of sine x over x is equal to 1, we conclude that a has to be equal to 1. Okay, so now we have two expressions for sine x over x. On the one hand, we have this power series. On the other hand, we have this infinite product, right? So combining the two expressions, we have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, and so on, is equal to 1 minus x squared over pi squared, 1 minus x squared over 4 pi squared, x squared over 9 pi squared, and so on. Okay, so now, again, pretending that we were working with polynomials, what you would do, or what you could do, is you could multiply this side out and then compare coefficients of x to the 2n on this side and x to the 2n on that side. Right, so equating the coefficient of x to the 2n on the left-hand side and right-hand side gives an expression for the sum of 1 over k to the 2n. Right, so for example, the coefficient of x squared on the left-hand side is minus 1 over 3 factorial, which is minus 1 over 6. And on the right-hand side, okay, well, let's stare at the right-hand side. When are we going to get an x squared, right? Well, if you think that each of these products, each of these factors is going to contribute either the 1 or the minus x squared over something, we can only have one contribution of x squared over something, because if we had more than one, then we'd end up with x to the 4th. If we're only going to end up with x squared, then we have to have all of these factors contribute 1, except for one of the factors, which will contribute minus 1 over some multiple of pi squared, right? So that means that here we would end up with minus 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared, and so on. So minus 1 over pi squared times the sum 1 over k squared, where k goes from 1 to infinity, right? And setting these equal, we get that the sum k goes from 1 to infinity of 1 over k squared is equal to pi squared over 6. Right? That's the solution to the Bessel problem. And we'll stop there.